RF Man here. Today we're going to talk about transmission line transformers, or TLTs, that are used for impedance matching. You might recall from my first video of the video series, part 1, that this is the type of transformer that we're talking about, wound with low impedance coax and ferrite cores. So this is the kind that we'll be discussing. For high frequency, typically you only need to use low impedance coax without the ferrite cores, but at the high frequency range, the cores are needed to meet the minimum impedance requirements. And we're going to talk about that. So you probably recall from part 1, we talked about a conventional RF transformer. This particular transformer basically has a primary and secondary, and it uses electromagnetic induction to induce a voltage from one winding to the other. This can be used for stepping up the voltage or stepping down the voltage. And we discussed this in part 1. This provides galvanic isolation between the windings, so the primary and secondary are completely isolated. Now, if we look at a TLT transformer, there is no electromagnetic induction here. Okay, it uses what's called transverse electromagnetic line coupling, and we'll talk about that. It's in basically the transmission line mode, and there is no galvanic isolation, and there is no electromagnetic induction here. So let's take a little closer look at that and see what that actually means. So as I said, with conventional transformers, we have an electromagnetic flux that couples energy between the primary and secondary. In the TLT transformer, we're using a TEM transmission line mode. So basically, we have an electromagnetic wave that's propagating through the coax wire, and we're looking at basically the electric field and the magnetic field, which are perpendicular to one another. So that's what's illustrated here. Okay, we have our RF signal, and it's flowing through the coax, the transmission line, and it's propagating through the line at a particular wavelength. And we have the magnetic field and we have the electric field that are at 90 degrees from each other. Okay, so this is how this transformer works based on this principle. And if we take a quick look, we're going to be talking primarily about a Guanella transformer, a 4-to-1 and a 9-to-1. And if we look at Guanella's designs, we have basically a voltage column and a current column. These can be wound with ferrite and coax or ferrite and twisted pairs. And we can see that these are the building blocks that are used for these type of transformers to give us different ratios. So if we combine, for example, two 1-to-1 current columns, it'll produce a 4-to-1 TLT. And here are two examples. There are different configurations that are used here, okay? But this is typically what they look like. So let's take a deeper dive into this. This is a 4-to-1, so we typically use this for impedance transformation to go from 50 ohms, which is on the low impedance side, to 200 ohms, which would be on the high impedance side. And you can use different configurations to determine different impedance ratios. So here, on the input side, the windings are in parallel with each other. And on the output side, the windings are in series with each other. And this is a key point. This is how these transformers actually work. And we're going to look at this in detail when we talk about the 9-to-1 or 1-to-9 transformer that's used for an RF push-pull amplifier. But just briefly, what we're doing here is we're dividing the current but doubling the voltage. Okay, and then the voltage squared like the turns ratio squared is equal to the impedance ratio. And again, we'll talk about that a little more. So here we have half the impedance. Here we have 2 times the impedance. So that's what we need to understand at this point in the presentation. And we'll go and actually transform these type of schematics into something easier to read and easier to understand. So the Guanella TLT uses equal lengths of transmission line so that we have equal delays in each line. And why is that important? Because the voltage has to stay in phase, so we're adding the voltages. So this type of technique is referred to as an equal delay transmission line transformer. And that's key to keeping the voltage in phase. For the characteristic impedance, in this case 50 ohms of each transmission line, this results, as I said, in 2 times higher impedance on the output and half the impedance on the input. And the 2 currents that we have, right? We have currents in the 2 conductors. They are equal in magnitude, but opposite in phase. Okay, so that's called odd mode or differential mode, while the voltages across the 2 conductors are both equal in magnitude and equal in phase. This is called even mode or common mode. And this helps us to reduce the common mode currents in the input side and output side of the TLT. So we're going to take a much closer look at exactly how it divides the current and how it doubles the voltage and what all that means. Okay, this is just to show that for different configurations, you're going to see many different types of representations. Okay, either using schematic symbols for inductors or other symbols to depict the ferrite and the coax. And this can be expressed many different ways. And I think that's what adds to the confusion when we try to understand how do these transformers work, how do they transform the impedance from the input to the output. Very difficult to really grasp what's happening when you look at schematic drawings like this. Here, it's drawn as an auto transformer, which it's a special type of auto transformer because there's no isolation here between these windings. And as I said, you can see we have odd mode currents and even mode voltages. So we're going to take a closer look. So one other point before I move on, you can have these set up as either balanced to balanced or balanced to unbalanced. So I'm going to basically take a moment to explain that. I did show this in, I think, part 1 and part 2, but again, let's take a look. It never hurts to review it. So here we have an unbalanced input, right? So we have our signal to ground. Okay, and then the output is also unbalanced. So we have our signal and our ground. So that's unbalanced to unbalanced. The other version that we see, that this would be incidentally for a single-ended type of amplifier. And here we have balanced to unbalanced. So this would be basically for a push-pull amplifier, right, where we have 2 inputs, okay, and we have 180-degree phase shift, which I'm showing here, and we go from balanced to unbalanced, and we would typically use like a 1-to-1 column, like the one I showed on my circuit board here. This is what converts it from a balanced input to unbalanced here. So here's a schematic of my dual LDMOS board, and it's 1 to 9. So remember what we're doing here. We've got low impedance of our LDMOS transistors, and we have the high impedance of our load, which happens to be 50 ohms for an RF system. And you can see that this particular transformer is shown as a schematic drawing using the symbols for inductors. But another very common representation would be showing the TLT with these symbols for the ferrites and also for the coax, or could be twisted pair, whatever the case might be. But this is the application. So for the LDMOS transistors, we have a low impedance. Two of them together is about 5.56 ohms. Okay, and then we have to transform that to 50 ohms. So when you do the math, that's exactly a 1 to 9 impedance transformation. So how does it do that? How does it work? Okay, let's take a look at some of the theory first, and then we'll show you how to actually calculate the voltages and how it transforms the impedance into the 1 to 9 that we require for our push-pull amplifier. So TLT theory, the 9 to 1 or 1 to 9 Guanella transformer, as I said, is based on equal delay transformers. So the transmission line lengths are the same, and this ensures the voltages stay in phase because we're adding them. Okay, and the currents are out of phase. So we actually have twice the voltage but half the current. On the input side, okay, the transmission lines are connected in parallel. Okay, this means they share the same voltage, but the total current is divided by 3 in each branch. And the next diagram that I show will make this a lot clearer. On the output side, okay, the high impedance side, the transmission lines are connected in series. This means that the voltages sum together and give us that 9 to 1 ratio. And the ferrite materials that are typically used for TLT, they're pretty high, either material 28 or 43, as I show here. And these have a high permeability, and we need to have at least 10 times the load impedance, right? So if the load impedance is 50 ohms, then we want to, when we calculate the inductive reactance, we want to be about 500 ohms at the lowest worst case frequency. And the coax itself, it's similar to a quarter wave transformer, but in that we need to calculate what the requirements are for the actual cable. So what should the impedance of the coax cable actually be? And we calculate the geometric mean of the input and output loads. And typically, in order for the transformer to perform properly and at the proper bandwidth, we need to use low impedance coaxes like CT12 or CT18. And we'll show that in the upcoming slides. Okay, so this is our calculation here. Most TLTs use semi-rigid low impedance coax, okay, anywhere between 10 and 25 ohms. And also we use the same low impedance coax to design and build splitters and power combiners. And the length of the coax needs to be less than 1/8 of a waveform. So lambda 8, okay, or taking the wavelength and dividing by 8. And we'll talk why that is necessary. And let's just take a look at an example here. Okay, I'm going to use the center frequency of the high frequency band, which is 15 megahertz, right? If we go from let's just say 1 to 30 megahertz, we'll use 15. It's not that critical. As I mentioned, the output impedance of the two BLF 188 transistors is 5.56 ohms, and our transmission line is 50 ohms. So if we basically calculate, we take 50, which is the load impedance, times 5.56, which is our source impedance, and we take the square root and we round that off to 17 ohms, so that would be TC18 coax. And then the length, you're just calculating the length of an eighth of a waveform. So we take basically 300 divided by the frequency times an eighth of a wave, which is 0.125, and we get the physical length of 2.5 meters. That's our physical length. And then if we apply the velocity factor for this coax, it's 0.7. So if we take the physical length times 0.7, okay, we find that the electrical length would be 1.25 meters, okay? And if we convert that to feet, it's 5.7 feet. So the general practice here is for these type of transformers, just try to keep the coax as short as possible. It's relatively easy to get below this 5.7 feet. I think if you look at the total footage used, it's like 4 feet. So you just need to try to keep the coax cable shorter for high frequency. Now for VHF, you're actually calculating the eighth of a waveform. Let's say for 2 meters, 144 megahertz, okay, and now it's more like 14 centimeters. So you're trying to keep it just below the 14 centimeters. But with high frequency band, which is much lower in the frequency and wavelength, it's not that critical. Just keep it as short as possible. And so what does the total length have to be less than an eighth of a wave? Well, we want to avoid any resonant points. And any length of coax, if you put it on a VNA, is going to have a resonant point. So you want to avoid resonance in the frequency range and bandwidth that you're using. And you want to reduce any phase shifts so that you have an equal delay on each line. So that's why we use an eighth of a waveform or less in the length of the coax. And here's our example on this side. We're going from the low impedance side to the high impedance side. Okay, it's less than an eighth of a waveform, and we're using 17 ohm coax for the impedance transformation. Okay, so here's the 1 to 9. And if I go back to my schematic here, right? 1 to 9, so here's the two LDMOS transistors. We're at 5.56 ohms, so we got to go from a low impedance to a high impedance. So that's our 1 to 9 ratio. And then if we go ahead and look at these various designs, we'll see how that's done. So as I said, there are many different ways that these transformers are expressed. Okay, here we're using symbols. Here we're using a schematic symbol for inductors. And it can be quite confusing looking at this, but these are all equivalent, okay? So this diagram or this schematic are identical. And the best way and easiest way to really understand that is to number all the nodes. Okay, 1, 3, 2, 4, etc. Okay, and here we see that on this side we have nodes 3, 6, and 1. On this side we have nodes 7, 5, and 4. Okay, now if we look at our schematic, okay, we have also numbered all the nodes, and on this side we have nodes 6, 3, and 1, and here again 7, 5, and 4. So these two are identical, and then on the output we have 2 and 8, and here's 2 and 8, okay, and here's the other two windings, 4 and 6, and 4 and 6. So these are equivalent, and they're identical. All right, but this still is not completely clear on, okay, we said that on the input side, the windings are in parallel, and on the output side, they're in series. So it may not look that clear, so I went ahead and drew it again, okay, in a different form, okay, and I'm actually showing the parallel windings and the series windings. So here again, on the input side, it's parallel, and on the output side, it's series. So if we look at the numbers on the nodes, okay, we're going to see that nodes 6, 3, and 1 here are the same as this point and this point. And if we look at nodes 5, 4, and 7, okay, the numbering is not exactly the same, but the 3 nodes are. It doesn't matter on the sequence. So we have the same point here and same point here. So now it's very easy to see that on the input side, I actually have 3 parallel branches, and of course through the load. And what is that going to do? Well, let's take a closer look and see. Okay, so here's the same diagram. Okay, and here's our 3 parallel branches. And as I said, the input's in parallel, so it's going to divide the current equally, right? They're the same impedance, okay, at the same frequency, or you could say same resistance. Impedance is just AC resistance. And you see it divides the current through each branch, okay? So yes, the input side of the transformer is in fact in parallel when you express it this way. And here's our nodes, right? 3, 6, and 1, 5, 4, and 7. So it's identical. And then the outputs are 2 and 8. Okay, it's just a different way of expressing it, but it's much easier to see the parallel and series relationship. So here we divide our current, okay? But when we look at the output side, looking into the transformer, okay, we can see that 2 and 1 and 3 and 4 and 7 and 8 are actually in series, okay? So what does that do for us? Well, you know series resistance, right? If the resistors are the same, you're going to have an equal amount of voltage across each one. The voltage drops would be the same. So what you'd see here, okay, if we measured each branch, and we're actually going to do that, okay, we would see on the input 3 volts, then 6 volts, then 9 volts. Or if I go the other way, looking into the transformer, and that's incidentally how I'm going to test this because this side is unbalanced, and it's easier to do that way with your function generator. You're going to see that we'll have 9 volts, then 6 volts, then 3 volts. Okay, so this will step up the impedance using the voltage ratio. And like the turns ratio, remember, turns ratio squared is equal to the impedance ratio. So if the turns ratio is 3 and I square it and it's 9, that's my impedance ratio, 1 to 9. Well, voltage is exactly the same. Okay, so if I take the voltage, which the ratio would be here, 3, okay, and I square it, I get 1 to 9. So this is my test setup, and I'm going to actually demonstrate this live when we are done with this slide. So here I'm using an oscilloscope. I'm using my function generator. I'm going into the unbalanced side, and I'm actually going to measure the voltages, just as we had. I'm going to use 9 volts, like my example, and we'd have 9, 6, and 3, or I could use 3 volts, and then we'd have 3, 2, and 1. Same thing. It's a 3 to 1 voltage ratio. Square it gives us 9 to 1 impedance ratio. So this is the equipment we're using. This is the test setup. These are some of the preliminary measurements that I made, which I will be doing live. And maybe this helps to show where the connections are a little clearer. So we're going to go ahead and put this on pause and set this up on the bench and take some measurements. All right, so now I'm back. Got this all set up. Here's our function generator at 10 megahertz, 9 volts. Here's our oscilloscope so we can measure the corresponding waveforms. And here's our board set up. I'm going to be measuring the same 3 points that I showed on the schematic, okay, from the output side to the input side. So let's take a look at that. And then, of course, if we do it the other way around, we're going to get the same results. So let me reposition my camera and zoom in on the scope so you can see the measurements. So here we've got around maybe 8.96 volts. And then we go to the second point. We have 6 volts, 6.08 volts. And if we go to the third point, we have our 3 volts. So if we do that the opposite way, here's the 3 volts. And then we're going to go 6 volts. And then we'll go to 9 volts. So you can see the transformation that's happening. And basically, we're stepping up 3 volts to 9 volts, so that's a 3-to-1 voltage gain. And then 3 squared equals 9, and 9 would therefore be the impedance ratio. So that's the demonstration. Those are the measurements. Next, we're going to be looking at the return loss of this type of transformer on the VNA, and then look at how it performs in an actual amplifier. So let me set that up, and I'll be back. All right, so before we actually take a look at the performance of the TLT transformer on the NanoVNA, I noticed when I reviewed the second section of the video that you really couldn't see exactly where I was measuring. So what I did here is I took a picture of the board and then I numbered each of the nodes to match the schematic here. Okay, so for example, this inductor is node 6 and node 5. This inductor is node 3 and node 4. So you can see how that corresponds here. And these are my measurement points, okay, between 5 and 6, 3 volts, and then between 3 and 8, 6 volts, and then between 2 and 8, which would be these series resistors, we're measuring 9 volts. So that just makes it a little clearer on how I took the measurements on the board. And remember that the TLT is just a combination of series and parallel circuits. You can configure those to achieve all different kinds of ratios to match your load impedance to your source impedance, or source impedance to load impedance. So next we wanted to look at the TLT on the NanoVNA. Specifically, we'll be looking at it on the Smith chart, also looking at the SWRs and the return loss. Okay, now this is a measure of how much reflected power, so we'll be spending a little bit of time discussing that. So let me just quickly switch over here and show my setup. There's my board, and then there's the NanoVNA. I just happen to have a long cable, and I already had it calibrated, so I just used a longer cable. Remember that when you calibrate, you need to calibrate at the reference plane here. That's very important to get accurate measurements. I discussed that in several of my other videos. So let's go now and take a look live and see how this performs. I'm going to exit out of here. We're going to load up the software, and there we are live. And we'll go ahead and sweep this. Okay, and let's explain what's going on. I mentioned the Smith chart in many of my other presentations, but real quick, the top part of the chart is plus J, so that's inductive. The bottom part of the chart is minus J, so that's capacitive. The center of the chart is the non-reactive center or resistance. And at the very middle of the chart, here's our 50 ohms. So you see we have a nice tight circle around 50 ohms depending on the frequency. And if we look at the phase, what would we expect to see if I just move the frequency to the center of the chart? Okay, that's where we're at zero phase. And of course, if we go to the upper half of the chart, okay, which is inductive, okay, it's plus J, and if we go to the bottom half of the chart, it's minus J, and this would be capacitive. So just to look at the phase and understand that a little better. That's the relationship. But more importantly, this is our SWRs. So you can see as we sweep through the frequencies here, and I'm just reading up here on the chart, that's about 1.27. The center is about 1.18. And on the high end, we're about 1.39. So fairly flat SWRs. And I'm just using a simulated load, right? 50 divided by 9 is 5.56 ohms, and that's what we're using. With the actual transistor, you might have to do some additional tuning because you've got a real part and inductive part. So this is a good representation, though, and is extremely close to what you'd expect to see with an actual transistor. And this is a measure of return loss. So the more negative this is, the less reflected power you have. And typically for this type of design, minus 14 is considered excellent. So if we go to the low end, we're closer to minus 18. Go to around the middle of the band, minus 22, which is really good. And then up here, minus 14. So how do we know what's a good benchmark for return loss, which is our reflective power? There's actually publications out there, and I've included one of them in my presentation so you could see and compare. So that's the performance. SWR looks pretty good, pretty flat. The circle around 50 ohms on the Smith chart is good, and the return loss is excellent, especially in the middle of the band. Okay, so let me exit out of this. Go back to my presentation. And here's what I just mentioned. Here's some benchmarks for good designs and then excellent. So general design target would be minus 10 dB. Okay, for consumer electronics, minus 10 to minus 12. Excellent return loss would be minus 14 dB or greater. So you can see that we were at about little more than minus 14 dB. So it's performing very well. Test equipment 15 dB. This just gives you an idea of the benchmarks for return loss. And again, the lower the decibel level, the less return loss there will be. Okay, so the last part of the presentation, I'm going to look at my dual LD MOS board with the 1 to 9 TLT, and we're going to do some benchmarking against the Amplifier board. So this is with a BLF 188. This is the TLT that we've been working on. And here's the actual board with the transmission line transformer. And this has got two BLF 188s. I'm just using these clamps. This is only for testing in the lab, so these clamps are okay. They're not made for continuous duty, so just wanted to point that out. So that's my board, and I benchmarked this to see how it compared. So let's take a look. Here is the board on the spectrum analyzer at 1,000 watts. And basically the worst case frequency was the third harmonic, and I'm at minus 15 dB at 1,000 watts. Okay, and then we also took a look at the intermodulation distortion, or what's typically called IMD, and we were at minus 25 at 1,200 watts. This is a good measure for basically sideband, how much bandwidth you would occupy on each of the sidebands that you're transmitting on. So this is another good important data point, would be the two-tone test with the intermodulation distortion. And I have a separate video on this, and I'll post that under the video. I'll put the links, some of the relevant links that you can go back and check if you haven't seen these videos before. And okay, so now this is the Amplion reference design, also broadband, and it uses their version of a TLT transformer. It is also 1-to-9. And here you can see their design using toroids and low impedance coax. This is also 17 ohms, which is TC18. So it's the same coax that I'm using. And there's the layout. And here you can see their harmonics, okay, at 1,000 watts. I used the same power output so I could do a direct comparison. And you can see D3 here. This is about minus 14 dB. Mine was minus 15 dB, so I'm 1 dB better than Amplion's reference design. And here they just plotted the intermodulation distortion, which you see there, two-tone test, on a chart at various frequencies. But at 1,200 watts, it's also minus 25 dB. So same as my result. So benchmarking my board against the Amplion board, I think compared fairly well. And yeah, that's it. So this is just providing an overview on the TLT transformers. The main takeaway is that there is no electromagnetic induction on these transformers, and that basically they use a combination of parallel and series circuits to achieve the transformations that you need. So we looked at a 1-to-4 and a 1-to-9, but of course there's many others. Also, the same applies when using this technology and methodology for designing balums. So I have a video out there on a 1-to-9 balum, which I used for a long wire antenna. But this particular presentation focused specifically on transformation for push-pull amplifiers. So the topology that's used and the differences between each of the transformers, as I've shown in part 1 and part 2. So that's it. That's the presentation. RF Man. Thanks.